Here we're going to look at a nice infinite product which can be seen as a generalization or maybe in the same family as the Wallis product. So let's just recall that the Wallis product is a famous infinite product representation involving pi. So our goal here is to find this product as n goes from 1 to infinity. We've got 2n over 2n minus 1 quantity squared. We've got 10n minus 6 over 10n minus 1, and then 10n minus 4 over 10n plus 1. We're going to use a couple of tools to evaluate this infinite product. The first will be the infinite product representation of the sine function. And in fact, we'll prove this one first. The last two will involve some non-standard trigonometric values. So we're going to show that pi over a times sine of pi over a is equal to this infinite product of a times n quantity squared, an minus 1, an plus 1. Okay, so let's maybe get to this first. So we're going to use the following fact in order to prove this first tool. And that fact is going to be some infinite product representation of sine, but a little bit less specialized than this. So we've got sine of theta equals theta times this product n goes from 1 to infinity of 1 minus theta squared over n squared times pi squared. So I won't prove that, but I will give some motivation for why that is true. So we can think about this thing as some sort of infinite polynomial. What I mean by an infinite polynomial, it's like a polynomial with infinite degree. In other words, like a power series. But we have factored it in terms of all of its roots. So with roots at m times pi, where m is an integer. That's exactly what we have. So notice the 0 times pi root is given to us by the fact that we've got a theta term out front. And then all of the other roots at integer multiples of pi are given by this factorization 1 minus theta squared over n squared times pi squared. So for instance, if we plug in 5n for theta, or maybe 5 pi n for theta, so notice that's going to be canceled by the 5th term of the product. Then similarly, if we plug in like -7. Okay, great. So now what I'm going to do is take this, divide a theta over, and then take the reciprocal. So that's going to give me an equivalent representation. Sine of theta, well, theta over sine of theta is equal to this product as n goes from 1 to infinity of 1 over 1 minus theta squared over n squared times pi squared. Now I'd like to simplify this a little bit so that I have a less complicated fraction by multiplying the numerator and the reciprocal of this by n squared times pi squared. So let's see what that gives us. That's going to give us this product as n goes from 1 to infinity. N times pi quantity squared is how we'll write the numerator now. Then the denominator we will write as n times pi quantity squared minus theta squared. The next thing that we're going to do is evaluate this at a special value of theta, and we're going to look at the left-hand side of our desired tool, and notice if we evaluate this at theta equals pi over a, we're good to go. So let's evaluate this at theta equals pi over a and see what we get. So the left-hand side will be exactly pi over a times sine of pi over a. And now the right-hand side will be equal to the product n goes from 1 to infinity. We've got this n pi quantity squared over n pi quantity squared minus pi over a quantity squared. And we're almost there. Now the next thing that we're going to do is multiply the numerator and the denominator by a over pi squared. So if we multiply the numerator and the denominator by a over pi squared, let's see what happens. So we'll have this product, n goes from 1 to infinity. And then notice the pi squared and the pi squared will cancel in the numerator. We'll have n times a quantity squared. And then this pi and that pi will cancel. We'll have n times a quantity squared minus 1 squared, because pi over a times a over pi is 1. But now notice that we have achieved our first goal. Now we're ready to move on to our second goal, which is this value of sine at 2 pi over 5. And we'll actually develop a tool which will help us prove both of these values of sine. And that is, we will calculate the sine of pi over 5, then use the double angle formula and the half angle formula respectively for this and this. So the first thing that I want to use is the following fact, which is maybe like a quintuple angle formula for sine. So we've got sine of 5 theta is equal to 16 times sine to the 5th theta minus 20 times sine cubed theta plus 5 times sine theta. So I'm not going to prove that, but maybe we'll talk about how you would get at that. So maybe my favorite way to get at that would be to use the fact that e to the I theta is equal to cos theta plus I sine theta, so Euler's formula, and then also use the fact that if you raise this to the 5th power, you have e to the I 5 theta is equal to cosine 5 theta plus I sine 5 theta. So on the one hand, you can take this to the 5th power, and then on the other hand, you can use this over here, then compare real and imaginary parts, and you can get all sorts of trigonometric identities using this kind of idea. Okay, great. So now what I want to do is set theta equal to pi over 5 in this equation up here. And then we'll set x equal to sine of pi over 5, or sine of theta in this case. So notice that's going to give us a polynomial which we can solve for x. Notice if theta is pi over 5, then 5 times theta is pi, sine of pi is 0, and then we can replace all of these sine thetas with x's, giving us a quintic polynomial. So we have 16x to the 5th minus 20x cubed plus 5x equals 0. Now our goal is to find the roots of that polynomial. So notice, since we set x equal to sine pi over 5, we know that sine pi over 5 is not equal to 0 because we know exactly what the roots of sine are. That means that we can divide this whole thing by x without destroying our goal of calculating the sine of pi over 5. So we divide this equation by x. That's going to leave us with 16x to the 4th minus 20x squared plus 5 equals 0. In other words, we have a quadratic polynomial whose variable is x squared. So we can apply the quadratic formula to this. That'll give us x squared equals, so negative b. That'll be 20 plus minus the square root of b squared. So that's going to be 400 minus 4 times a times c. So 4 times this is 320 all over 2a. So that's going to be 32. Good. So now the next thing that I want to notice is that these two guys add up to 80, which is equal to 16 times 5. So now we can rewrite this as 20 plus minus 4 times the square root of 5 over 32, where I brought this 16 out of the square root by taking its square root. Square root of 16 is 4. Now what I want to do is cancel this as much as I can. I will have 5 plus minus the square root of 5 over 8. Now we have to decide, to achieve our goal, do we need to take the positive sign or the negative sign? And I'm going to say that you have to take the minus sign. And you can see that by arguing something about the size of sine of pi over 5. So maybe comment why you have to take the minus sign and not the plus sign, and we'll see that. Okay, so now we can take the square root of both sides, and we'll get x equals the square root of 5 minus the square root of 5 over 8. In other words, sine of pi over 5 is equal to this, where again we took the positive square root. Here it's a little bit simpler because we know that sine of pi over 5 should be positive. Okay, let's go ahead and bring that up, and then we will use this to calculate these two values. So we just got done proving that the sine of pi over 5 was equal to the square root of 5 minus the square root of 5 over 8. Now we want to employ the half angle formula and the double angle formula to get the sine of 2 pi over 5 and the sine of pi over 10. So let's maybe recall really quick that sine of 2 theta is equal to 2 times cos theta times sine theta. So we're going to want to use this formula together with theta equals pi over 5. So the first thing that I want to do is use the Pythagorean identity to calculate the cosine of pi over 5. So it's going to be the square root of 1 minus the sine of pi over 5 squared. So in other words, this is going to be the square root of 1 minus this thing right here, but with no square root, because we had to square root it. So that comes from the fact that cosine squared plus sine squared is equal to 1. Okay, so now let's go ahead and simplify this. We can replace this 1 with an 8 over 8. Then we can think about distributing that minus sign through. So we'll have 8 minus 5, so that's equal to 3, minus negative root 5, so that's going to be plus root 5 all over 8. Good. Now what we want to do is apply this formula. So now we've got sine of 2 pi over 5 will be equal to, so it's going to be 2 times this cosine, so that'll be 3 plus root 5 over 8, and all of that is under a square root, times this sine, so that'll be 5 minus root 5 over 8. Good. Now let's go ahead and simplify this a little bit. So I'm going to go ahead and bring this 8 out because we've got 2 of them under a radical. That's going to give me 1/4, and then I'll have the square root of 3 plus root 5 times 5 minus root 5. So we need to multiply out that. So the rational part is what we'll take care of first. So we get the rational part of this interior by 3 times 5, which is 15, minus root 5 times root 5, which is 5, so we've got 10. And then the irrational, or the square root of 5 part, will be root 5 times 5, so that's 5 root 5 minus 3 root 5, so that's going to be plus 2 root 5. Great. Now next what I want to do is bring this 1/4 inside, but if I bring that 1/4 inside, I have to turn it into a 16 because we need to square it. But now we can easily simplify this to the square root of 5 plus the square root of 5 all over 8, which was exactly what we wanted for this second goal. Now this next one is going to go very, very similarly using the half angle formula instead of the double angle formula. So I'll let you guys check that on your own. Maybe post in the comments if anything tricky comes up, but I think it should be pretty straightforward. So we've taken care of this. Now we're ready to evaluate our goal product. And we're going to do that by making heavy use of this first tool, and then the last couple of steps will be governed by these last 2 tools. So since I want to use this first tool quite a bit, I need to rewrite this so that I have a bunch of terms that look like this over here. And I'm going to do that by multiplying by special versions of 1. But maybe before I do that, let's write everything out. So we've got this product as n goes from 1 to infinity. I'm going to write this as 2n quantity squared over 2n minus 1 quantity squared. The next thing that I want to notice is that in order to use this, I've got a 2n minus 1, but now I need a 2n plus 1. So I will multiply by that version of 1. So 2n plus 1 over 2n plus 1. Okay, good. Now the next thing that I want to notice is that I've got this 10n minus 1 times 10n plus 1 term. So let's go ahead and write that in the denominator. That is actually part of our product already. So 10n minus 1, 10n plus 1. But in order to make use of this, I need something in the numerator that looks like that. So I'll need a 10n quantity squared in the numerator. Okay, good. But that means that I'm going to need to add a 10n squared in the denominator as well. So let's maybe go ahead and do that. We've got a 10n squared in the denominator as well. Now let's notice that we've got a 10n minus 4 term already. So I'll put that up here, 10n minus 4. But we probably want a 10n plus 4 to, again, make use of this right here. So let's go ahead and include that. So 10n plus 4, but that means we need one of those in the denominator as well. So let's go ahead and put that down here, so 10n plus 4. So notice that we've multiplied by this version of 1, this version of 1, and this version of 1. So now let's see what we haven't taken care of. So now we've included all of our original terms, 3 new types of terms. We just need a 10n minus 6. That's the only thing that we're missing. So let's write that up here, 10n minus 6. So now let's go ahead and partition this into pieces that can be evaluated using this first tool. So maybe the first thing that we'll do is notice that this is going to be the product. N goes from 1 to infinity. We have 2n quantity squared over 2n minus 1 times 2n plus 1. Good. So that's most definitely of this first type. So let's see what we can do next. We've got this 10n quantity squared over 10n plus 1, 10n minus 1. That's also of this form. So let's write that down. So 10n quantity squared over 10n plus 1 times 10n minus 1. So that'll be useful as well. Now let's look at what we have next. We've got this 10n minus 4 and this 10n plus 4. And then we've got a 10n quantity squared in the denominator. So we can actually make use of this formula again if we factor a 4 out of each of those terms. But we can factor a 4 out of each of those terms if we bring it down into the denominator here. So let's maybe go ahead and do that. So this is going to be 10 over 4n minus 1, 10 over 4n plus 1, all over 10 over 4n quantity squared. So now we've taken care of almost everything. The only thing that's left over is one of these 2n minus 1s, a 2n plus 1 in the numerator, a 10n minus 6 in the numerator, and then a 10n plus 4 in the denominator. So let's maybe go ahead and fit that in right here. So we'll have a 2n plus 1, a 2n minus 1 from one of those, and then a 10n plus 4, and then finally a 10n minus 6. So that's what's left over after grouping all of these together. So let's notice that this one right here in white will be equal to pi over 2 times sine of pi over 2. Because this is exactly this format right here with just a equals 2. Now let's go ahead and see what this yellow one is. So notice that yellow one is exactly the same where a equals 10. So this is going to be pi over 10 times sine of pi over 10. The next thing that I want to notice is that this pink term looks like the reciprocal of our formula where a is equal to 2 over 5. And so we can replace it as such. So this is going to be replaced with 5 times the sine of 2 pi over 5 over 2 pi. Again, just using the reciprocal of this formula. And then all of this stuff in purple is still within the product because it does not fit the form of this guy over here. So we're going to have to take care of that on its own. So now we've got this product as n goes from 1 to infinity. So we've got 2n plus 1 and then 10n minus 6 over 2n minus 1 and then 10n plus 4. So now let's simplify this as much as we can. So maybe notice that this 10 and this 5 cancel down to have a 2 here. And then this pi and this pi cancel. And then furthermore, we know that the sine of pi over 2 is 1. So let's see what that gives us. So that gives us pi over 2 for this first term. And then we're going to have 1 over 2 times the sine of pi over 10. But notice we know what sine of pi over 10 is this 1 over 4 times that. And so notice the 2 in the denominator and the 1 over 4 in the denominator, we'll put a 2 in the numerator. And then we have negative 1 plus the square root of 5. So again, that's this part that's in yellow. Great. And then next, we've got a 2 in the denominator and then sine of 2 pi over 5. So notice that sine of 2 pi over 5 is this thing right here. but then we also have a 2 in the denominator, so that's going to be equal to 1/2, and then the square root of 5 plus the square root of 5 over 8. So just to reiterate, that's our pink part right here. Okay, and then finally next, we have this product, n goes from 1 to infinity, of 2n plus 1 over 2n minus 1 times 10n minus 6 over 10n plus 4. So now let's see if we can simplify this a little bit. So notice this first term can be multiplied by 1 plus the square root of 5 in the numerator and the denominator. So that's like rationalizing the denominator, if you will. And that's going to give us, so we'll have pi over 2 out front. And then notice that this is going to be equal to 5 minus 1, or 4 in the denominator. That 4 is going to cancel this 2 down to a 2, leaving us with a 2 in the denominator and then a 1 plus root 5 in the numerator. So now let's see what we can do with this next term. So I'll split this 8 up into 4 times 2. I'll bring the 4 out of the radical and it'll become 1/4 after multiplying with the 2. And now I'm going to have the square root of, I'm going to replace this 5 with a 4 plus 1. So we have 4 plus 1 plus root 5. And now each of those are over 2. So I've got something like that. And then next, I'll just rewrite this product. So we have the product as n goes from 1 to infinity. 2n plus 1 times 10n minus 6 over 2n minus 1. And then 10n plus 4. Great. Now maybe that's a good place to stop this board. I'll bring that to the top and we'll move on to the next step. So in the last board we ended at this point. Now we're going to simplify this a little bit. So the first thing that I want to notice is 1 plus root 5 over 2, that's the golden ratio. So I can bring this pi over 2 down and then write this as the golden ratio, which I'll call phi. Then next, I have that as times 1/4, and now I have the square root of 2 plus, well, that's the golden ratio again, so that's going to be 2 plus phi. And then the next thing that I want to do is simplify this a little bit. So notice that I can take a 2 out of the numerator and the denominator here. That's going to give me this product as n goes from 1 to infinity of 2n plus 1, and now this is going to be 5n minus 3 all over, so this is going to be 2n minus 1, and then the next one is going to be 5n plus 2. Great. Now we're going to take this thing and simplify it a little bit. So the first thing that I want to do is notice that this can be written as 1 plus 1 plus phi. Obviously 2 is 1 plus 1, and then I can take this 1 plus phi and write it as phi squared. Okay. Then I can bring all of this down with some of that simplification. So I've got pi times phi all over 8. So that would be this 4 times 2. And then next I have the square root of 1 plus phi squared. Now we're going to further simplify that a little bit, but we'll leave it like that for now. Okay, so the next thing that I'm going to do is rewrite this as a limit of a partial product. So I'm going to write this as the limit as m approaches infinity of this product as n goes from 1 to m of 2n plus 1 times 5n minus 3 over 2n minus 1 and then 5n plus 2. Good. Now next what I want to do is go ahead and take this thing inside of the radical, and I will factor a phi out of it. So I'll factor a phi out of this. And notice if I do that, I'm left with phi plus 1 over phi. Good. And then maybe like over here on the side, we can recall that phi equals 1 plus root 5 over 2, and 1 over phi equals negative 1 plus root 5 over 2. So that means if you add phi and 1 over phi, you're just going to get root 5. So that allows us to simplify the inside of this as well. So let's maybe go ahead and do that. So we're going to have pi over 8 times phi times the square root of phi times the square root of 5. Where the square root of phi came from this one right here, then the square root of 5 came from this right here, recalling these kind of setups. Nice. Now the next thing that I'm going to do is notice I've got this limit as m goes to infinity. And now I'm going to cut corners a little bit, but what I want to do is find this partial product and notice that it telescopes. So I'll put the first couple of terms and the last couple of terms, and we'll see the action that happens. So maybe we'll do the n equals 1, the n equals 2 terms, and then we'll do the n equals m minus 1 and the n equals m terms. So that's the first two and the last two terms. And I think that should be enough structure to see what's going on. So notice if we set n equal to 1, we will have 3 times 2. So 3 times 2 over 1 times 7. So 1 times 7. So that's the n equals 1 case. Now the n equals 2 case, that's going to be equal to 5 times 7 over, so let's see what we get. We're going to have 3 times 12. 3 times 12. Good. Now let's look at the m minus 1 case. So if we plug in n equals m minus 1 here, we'll have 2m minus 1. And then notice for that one, we will have 5n minus 8. Great. And then in the denominator, we'll have 2n minus 3, 2m minus 3, I should say. And then we'll have 5m minus 3. Great. And then our last term, which is n equals m, well, that's just going to be exactly this, but we switched n's with m's. So here we have 2n plus 1, 5n minus 3 over 2n minus 1, 5n plus 2. Now let's see what kind of obviously cancels. So notice this 3 is going to cancel with this 3. The 5 is going to cancel with something that comes next, and then so on and so forth. And then finally, this 2m minus 3 is going to cancel with something that comes before it. This 2m minus 1 is going to cancel with that thing that comes after it. And then notice that this 5m minus 3 is going to cancel with this 5m minus 3, and this 5m minus 8 is going to cancel with something that comes before it. And then finally, this 7 cancels with this 7, and this 12 is going to cancel with something that comes after it. So we're going to be left with pi over 8, and now we have phi times the square root of phi times the square root of 5. The limit as m approaches infinity of, let's see what we've got. We've got 2 times 2n plus 1, so that's going to be 4n plus 2 over 5n plus 2. But now that, that should be m. And these should be m's as well. But now that's a fairly simple limit to take. Notice we get the leading term in the numerator divided by the leading term in the denominator. So that's going to give us 4 over 5. This 4 can come out and cancel this to give us pi over 2, and then we've got a 5 in the denominator. So let's see what we're left with. We're left with pi halves, and then we have phi over 5 times the square root of phi times the square root of 5. Good. And that's our final answer. And that's a good place to stop.